Hello and welcome to the second part of this video series on density of states. In this video, we will look at the definition of density of states. Then we will derive the density of states for the frequency or the K domain. And finally, we will derive the density of states in the energy domain, which is our domain of interest. Both of these derivations will be done for a one-dimensional crystal lattice. So let's get started. The word density is usually linked with the heaviness of an object, and so it is defined as the ratio of mass to the volume of the object. But we intuitively use the word density in broader areas where quantities other than mass or volume are involved. For example, this is a map of population density by country, and it is defined as the ratio of total number of people living in a given area. So we can see that without using mass or volume, a density term is defined in this case, which means that we understand that density is more related to concentration of a quantity with respect to some other quantity. And so when we define density of states, we look at how concentrated the states are in the energy domain. The term energy domain is very important here. Now let me explain this definition with the help of an example. Consider this is a figure which shows electron states as a function of energy. So this horizontal axis represents the energy of states, while these green dots represent the points in the energy axis where the states exist. Now let's define some variables to analyze this graph. So we will say n is the total number of states in a given energy zone, and E is the variable which represents the energy of states. Now let's see, if I want to find the concentration of states or the density of states in a given zone, let's say this is my zone, then how will I find it out? So I will have to know the total number of states in this region. Let's call them some ns, and then I will divide it by the length of this region. Let's call it es. So the density of states in this particular zone will be a ratio of ns by es. Now I want to find the density of states at a particular point. So this point can be represented by the variable E. So density of states at any point E in this domain. So to find this, I will have to reduce the length of this zone to a very small value. Let's call it dE. So dE represents a very small value, and then the number of states in this small zone will become dN. So what I'm trying to do is I'm trying to construct a very small zone around this point which has a length of dE. So the density of states around this point will become dN by dE. Now I multiply this ratio by a factor of 2 because at every state a maximum of 2 electrons can be accommodated. We looked at this in the last video, which is related to the Pauli's exclusion principle. And then we divide this ratio with the volume of the crystal. Now please remember that this volume comes from the real space and not from the K space or energy space, and it is usually constant for a given crystal. So what we are more interested in is this ratio of dN by dE. Now that we have defined what is density of states, let's move to the next part of this video, which is derivation of density of states in the K domain, which is also known as the frequency domain. For that, let's have a quick revision of the things that we learned in the last video. So we looked at a one-dimensional crystal lattice of length L, which is shown in this figure, and then we saw what are the possible electron wave functions that can be accommodated on this lattice, and we represented these waves by these different colored sine waves, and then we plotted the frequencies of these sine waves on the frequency axis or the k domain, which is shown in this particular figure. Now, similar to how we defined the density of states for the energy domain, we can define the density of states in the k domain. Let's say at any point k, the density of states at any point k will be to build a very small zone around this point, which will have a width of dk, and the total number of states in that zone will be dn. So the density of states will now become dn by dk. Again, we will multiply it by the same constant, which is the 2 by volume of the crystal. Now that we already know how the states are distributed in the k domain, we can directly find the density of states for the k domain. One observation that we made in the last video was the distance between two consecutive states in this domain is always constant, and this distance is equal to pi by L. So now here's a question. How does that affect the concentration of states in the k domain? Well, the answer is that as I move ahead in the k space, the consecutive distance between two states still remains constant, which means that the concentration of states is not changing. Or I can qualitatively say that the density of states, which is also the concentration of states, for this one-dimensional lattice in the k space should be a constant. But now let's try to prove this mathematically, and let's try to find out what is the value of this density of states. So what we are interested in is this dn by dk. So let's try to find the relation between this n and k. Now I have drawn a table in which I will update the values for n and k. When k was pi by L, so the distance in the k domain was pi by L, how many states were there in this distance? So there was this one state. So for a distance of pi by L, the total number of states were 1. Now when the distance was increased to 2 pi by L, total number of states were this 1 and 2. So 2 states in the distance of 2 pi by L. Similarly, in the distance of 3 pi by L, there were a total of 1, 2 and 3 states. Now you see there is a relation forming between this n and k. If the value of k is some n into pi by L, then our capital N becomes this n. So we can write a equation between n and k. K is equal to pi by L into n. So pi by L into n, or n is equal to L by pi into k, which means that dn by dk will become L by pi. So the density of states for this particular case in the k domain will become dn by dk into 2 by volume. But as this is a one-dimensional lattice, we only consider the length part of it. So it will become 2 by pi, which is a constant. And this is what we expected by looking at this particular graph. Now let's move to the last part of this video, which is to derive the density of states in the energy domain. For that, we need to know how the states are distributed in the energy domain. And the relation between energy and frequency of a electron state is given by this famous equation, which is also derived from the infinite potential well problem. It states that for every state which has a frequency of Kn, there is one corresponding state in the energy domain which can be called as En. As we know all the possible states in the K domain, now we can find a corresponding energy for every value of K in the energy domain. So let's do that one by one. The first state in the energy domain, let's call it as E1, which will correspond to the frequency of K1, will have a value of h bar square by 2m into K1 square, but the value of K1 is pi by L. So it will be pi by L square. Let's call this value as some A. Now the second state in the energy domain, which will correspond to K2, will be h bar square by 2m into the second state, which is 2 pi by L square. So it will be 4 into A. Similarly, the value of E3 will be 9A, as K3 is 3 pi by L. In a similar way, we can find the value of En, which will correspond to Kn, as n square into A. Now let's try to plot these values in the energy domain. As all the values have A as their common multiple, let's keep our unit distance equal to A. The first state will be at a distance of A. Then the next state will be at a distance of 4A. Next at 9A. And so on. So this is how the states distribution will look like in the energy domain. Now let's try to analyze this graph a bit. You can see that the distance between two consecutive states in the energy domain is no more constant. So it was some 3A for the first two states, and it became almost 9A for the fourth and fifth state. And as I go ahead in the energy domain, this distance will keep on increasing, opposite to what we saw in the K domain, where this distance was constant. So here's a question: how does this affect the concentration or the density of states? So the answer is, as I move ahead in the energy domain, my states are getting less and less concentrated, or their density is decreasing. So I can qualitatively say that the density of states for this particular crystal in the energy domain is a function of some negative power of energy, as it is decreasing with increasing energy. But now let's try to prove this mathematically and find the relation. So again, what we are looking for is this dN by dE. Again, I have drawn this table and I'll try to find a relation between this capital N and E. Now, when the length was A, total number of states in this length was 1, which was at this particular position. When the length was increased to 4A, total number of states in this length became 2. So this one and this one. Now when my distance was increased to a value of 9A, then there were a total of 3 states in this distance. Now again there is a relation forming between N and E. So when E is some N square into A, then the capital N becomes N. Or we can write down the relation as E is A into square of this N. So N square, or N is equal to root of E by A, which means dN by dE will become 1 by 2 into A. Now if I substitute the value of A in this equation, then the dN by dE will now become if we substitute the value of h bar as h divided by 2 pi, so the density of states for this particular case, which is defined as dn by de into 2 by volume, but it is a one-dimensional crystal, so just the length will now become, so it is proportional to minus half power of the energy, which is what we predicted by looking at this particular graph. In this video, I've tried to explain the concept of density of states in a simple and graphical way. So I really hope that now you understand this concept better. And thank you so much for watching the video till the end.